ఇలా ఉంటారు పువ్వు అంటే ఇలాగైతే
అదే లింక్ సార్ ఉన్నారు ఆల్రెడీ
వాట్సాప్
రాజు గారు
రాజు గారు
రాజు గారు
chemistry and IT training practical insights from their presentation. Welcome, sir. Now I hand over to Mike to the chairperson of the session.
Sir. Sir, start chasing, sir. Sir, live lo unnaru, sir. I'm joining lo unnaru, sir. Start chasing, sir.
My slide is visible.
Amma, pressure silent kunandi. Ray, aapni maatladandi.
Hello. After his PhD degree from IIT Delhi in the area of nanosciences and nanotechnology in October 2007. During his research work, he has synthesized many oxide nanomaterials of titanates, zirconates, antanates, and neobates, and well characterized by advanced techniques. The dielectric properties have been studied for all the materials and optimized by doping of the nano counterparts to the pulp. After becoming a full assistant professor in the Department of Chemistry at NIT Warangal, during month of July 2008, he has been associated with the research in the area of photocatalysis. His recent significant contribution is carrying out the research work on design and development of novel photocatalysts for environmental remediation and hydrogen generation. He has published research articles in highly reputed journals like Journal of Materials Chemistry A, Journal of Physical Chemistry C, Physical Chemistry and Chemical Physics, Darton Transaction. His current interest is in design and development of suitable band gap materials for environmental remediation, green hydrogen generation, and nitrogen fixation. Research activity. He has awarded 5 PhD and PDF students and 6+1 ongoing. He has completed 3 projects. Department of Science and Technology, Government of India. The details of students supervised. Mr. Santosh K.R., Department of Novel GC3L4 based hybrid nano composites for photocatalytic applications under visible light. Mr. T. Surinder, synthesis and characterization of highly efficient nanostructured materials for photocatalytic applications under significant sunlight irradiation. Mr. Sai Kumar, fabrication of high potential nanocarbon based photocatalysts for hydrogen generation under sunlight illumination. Mr. Salem. Studies on dielectric and ferroelectric properties of lead-free barium, calcium, titanium, zirconium oxide, thin films and bulk ceramics. G. Ambedkar, development of highly efficient G3 based metal oxide nanocomposites for photocatalytic applications. He is member of many national and international science societies. Some of them are member of American Chemical Society, USA, member of Royal Society of Chemistry, UK, Indian Association Solid State Chemistry and Allied Scientists, Jammu, Associate Editor of Journal of Nanoscience Letters, reviewer of many science journals like Nanoscale, Advanced Fundamental Materials, Journal of Material Chemistry, Chemical Communication, Langmuir Inorganic Chemistry, Applied Materials Interface, Applied Surface Science, Catalysis Science and Technology, Journal of Environmental Chemical Engineering, RSC Advances, Bulletin of Material Sciences. Books published. Sai Kumar Manchala, Vijay Kumar, Yeliyappan, Hai Gun Lee. All these are under Vishnu Sankasa's guidance. Published books are plasmonic photocatalysis, an extraordinary way to harvest visible light. Photocatalytic systems by design, materials, mechanisms, and applications. P. Kiran Kumar, P. Venkateswara Rao, Sashi Vinay Kumar, Ravi Arukula, under Vishnu Sankasa's guidance, heterogeneous photocatalysis by graphite carbon nitride for effective hydrogen production. Materials for hydrogen production, conversion and storage. Thank you.
Hello. Hello. Is it audible?
Yes, sir.
My slide is visible?
Yes, sir. Yes, sir.
Yes, sir.
Okay. Okay, fine. So thank you for giving the opportunity. And my talk is basically on the fundamentals of nanomaterials and synthetic methodology. So while seeing the topic, it is I observe it is chosen very correctly, and it's fine-tuned with that current what the research is going on in the field of nanoscience and technology. So basically, in that my talk is based on the fundamentals of the nanomaterials, and a little bit I will touch about that its synthetic methodology and plus some applications. Right now, coming to that nanomaterials, the first it will come to that like in the mind, like why it is nanomaterials and what basically what the application of the nanomaterials. So before that, like first we have to try to understand like what is basically nanomaterials. So nanomaterials, if you see that the word, it is a coin of two words, that is a nano and materials. So nano basically it is, you can say it is a dwarf, it is a small, so, and materials means the whatever the material you'll choose for the application, that one. So basically the materials which you are choosing and the base of that, or the basic unit of that materials, if it is there in the nano range, then you can say it is a nanomaterials of that. So basically we are talking about here the materials which the basic unit, it comes under the nanoscale range. So that you can say it is a nanomaterials. Now come to the question, how to understand where it stands, that nanomaterials. So if you, let's see the nanomaterials where it stands. So basically if you look it into just for comparison, our planet Earth, and if you compare with the football, so you can see that it is a uh, 10 million times smaller than Earth if you compare that planet and football. And if you compare with fullerene, you know that it is a C16. So C16 is a carbon a molecule, and that size is, it is a 1 billion times smaller than the football. So you can say, you can just imagine that how it is, where we are talking about it. So we are talking about that it is at a smaller level, that is the assembly of the atoms, right? So when it is arranged in a proper way, then you can get some functionality of that of the molecules, of the materials. So that's, we are going to talk about it, like how it will change their properties. Now, further comparison, if you compare with that hair or your with hair, so just you can see that your hair size is, and if you look it into your the natural material, for example, it is a DNA. So if you compare that, so how so small it is. So your hair size is, it is around 10 to the power 5 nanometer, whereas your DNA example is, it is a 2 nanometer. So you can just see that if you compare it, how, where we are talking about it. Further, if you see that nature made material, the naturally available, and further that is a scientist synthesized material. So in that context, if you look it into that, so it is a DNA, proteins, and virus there, and that is a nature made. So it is a natural material. And if you look it into that, the man-made, so it is a basically C60, carbon nanotube, silver nanoparticle, all that. Okay, and it is having that some applications in that. So over a period, it is a lot of application it is developed.
అది మన కంటికి కనిపిస్తుందా?
I am audible.
అదే అంటే అదంటే పిక్చర్ లో చూపిస్తున్నాడు అంతే.
I am audible.
Yes, sir.
Okay. So now in that, the first where the world like start to thinking about the nanoscale, when the great scientist that Richard Feynman has delivered his lecture, that is a novel lecture on that there is a plenty of room at the bottom. So that means when you talk about at the bottom scale level, so means it the small size level, then you can like lot of opportunity there, lot of things you can do that. So basically that is the things you can exploit there, and you can make several possibilities there. And if you can like atom by atom, if you do that, and you can assemble that atoms and make a molecules which that control itself and like show the unique properties of that. So that's why it is a great opportunity there. And this great scientist, he has delivered, and he got the Nobel Prize in 1965. Now coming to the part of that, what happened when the size is reduces. So we are here, I will talk about some properties. Firstly, magnetic properties of that. So magnetic properties, basically, you know that it is a dipole alignment, right? So the dipole alignment, when it is a perfect aligned is there, so you can get the magnetic maximum magnetic behavior of that, right? So and also it depends on that how it is aligned that. Okay, so parallel, anti-parallel, all that. Now the thing is, if you look at into the any particle, if you look it into that, so basically you will have a that is a bulk, means core particle, core volume, and over that it will be there the grain boundary, right? So every particle will have their grain boundary, or you can say that every grain have their grain boundary of that. And the grain boundary and the core, it is a dipole arrangement, it will be different. So dipole arrangement in the core and dipole arrangement in the grain boundary, it will be different. So the grain bond in the grain boundary, the dipole arrangement, it will be random arrangement will be there, whereas in the core, the dipole arrangement, it will be perfectly aligned. So that's why here the properties that control that. So whatever the in the bulk size particle, the properties you are getting, it is a net dipole moment you are getting, where it is controlled by the core volume. Okay, now just think about it. When you reduce the size, when you are going to the from millimeter to micrometer to the nanometer. So if you are going towards that, the moment you reach to the nanometer, so what will happen? Your core volume, it will vanish, and it will be like your grain boundary, it will be like dominate. Okay, so in that case, what will happen? Your random dipole arrangement, it will be predominant. So that means your magnetic properties at the nanometer scale, it will be entirely different from the bulk. So that's why here the magnetic behavior, it will change if you compare with the bulk size particle. Bulk size, I'm referring to the bigger size particle, and nano size particle. When it is come to the nanoscale range, right? So this is the one where you are seeing that the change in the magnetic behavior of that. Coming to that, another example of that is the surface change of the surface area of that. So you know that in the catalytic activity, surface area is very, very important. So when the surface area increases, the catalytic activity also increases. So what happened when this size, it is from bulk, you are going to the nanometer scale. So when you are going from bulk to the nanometer scale, the surface area predominantly it is greatly changed. So it is a like drastically it is changed, it is enhanced. So great increment there in their value, and because of that you can say it is a activity, the chemical activity, it greatly change, right? For example, here also it is given in the cartoon image. As you can see that, here is the gold bulk particle is there. In the bulk particle, where you can see that the carbon monoxide, it cannot be get oxidized to the carbon dioxide. But when you change to the gold nanoparticle, so gold nanoparticle, it can able to oxidize carbon monoxide to carbon dioxide. So this is due to the highly chemically reactive the gold nanoparticle, right? And this is you are getting because of the high surface area of that. So high surface area will get a high surface energy of that. Now coming to the another properties, that is the electronic properties. So electronic properties, you know that it is a, if you like for example, if you are having that one example for the metal, another example for the semiconducting material. So in the conducting material, you know that there will be continuation band gap band, it will be there. So conduction, you will have a valence band and conduction band, and that it will be overlap each other. And so in the bulk, this is the basically condition you will get. But if you compare with the atomic scale level, so atomic scale level, you know that it will be discrete energy level. So going from the atomic scale level to the bulk state, to the bulk energy state, you see that there is a lot of change it is there. In the atomic scale level, it is a discrete energy level, whereas if you are going to the bulk, there is a continuation, you are finding the bands. Okay, but what will happen in the nano? So the nano, you see that it is an in-between state of that. So where you are having the band structure as well as there is a discrete energy levels also there, it is introduced. That's why it is a the properties, it is controlled by this kind of that electronic structure. Okay, coming to the semiconducting material. So semiconducting material also same thing, it is happening. So if you look at into that, the nano in the nano structure, so nanostructure material, semiconductor. So what happened here also, it is introduced the continuous band gap as well as you are having the discrete energy levels also it is introduced. So that's why here that the quantum it will come into the picture, quantum confinement. So as you see that here, so one properties you can see that here, the optical properties, it is changed. So as you see that when you are moving from the band structure to the quantum confinement, as you see that the band plus the discrete energy level. So as you see, there is a change in the optical properties. So you see here the color change of the material, right? So as you move down to the nanoscale, you can say it is a like blue shift you can observe in the material, right? So another example, for example, gold. So gold nano particle, if you compare with the gold, so bulk gold, as everyone know that it is a gold color of that. But when you make it into the nanoscale, nanocolloidal gold nanoparticle, then you will get the variety of color. So people will surprise that those doesn't know the science behind it. They will surprise whether it is a gold or not. But that you can make it. So you can synthesize the various size of gold nanoparticle, and you can get the variety of like color colloidal solution. That is another example you can show that that is a effect of nano. Another physical properties, for example, the gold nanoparticle. So the melting point of gold nanoparticle, if you look it into that, so it is a like 340 Kelvin if you are having the 2 nanometer size gold particle. Whereas for the bulk, you see that the melting point is very high. So that's why when you are moving from the bulk to nano, the drastic change is there in the melting point. Another example like ferroelectric, the barium titanate is well-known ferroelectric material, and their ferroelectricity also it affect by changing the size of the particle. So then now the question, I think it is clear why you are going towards the nano. So it is there is a lot of advantage there, a lot of applications there. So that's why we are going towards the nano. So one thing we have understand like their properties when it is changing, just change the size of that, because you are not changing the material. Material is same, only thing you are changing the size of the basic unit of the material. So that's why you are getting the different the material, it behave in entirely different, right? So that is the advantage here. Application that we will see later. So as you see here, so the chemistry point of view, you are getting the high reactivity of that material, like mechanical. If you see that, you are getting the better mechanical strength. Physics point of view, you are getting the it is a quantum effect there you are getting. So you are getting like lot of based on the physics, as you say that you can tune the material, you can tune the properties of the materials, and you can get the appropriate properties of that. So coming to that now, it will come that what types of nanomaterials there. So basically there is a two, you can classify one classification based on that the availability of the materials. So it is a availability, one is nature made material, so you can say the natural nanomaterials. Another one is artificial nanomaterials, so man made material, right? So nature material, already there are so many examples are there, like you are having that milk is there, blood is there, fog is there, gelatin is there, right? So those are, it is like a natural material. Artificial material, the carbon nanotube, carbon quantum dots, you are having the graphene, gravitic C3 and 4. There are several materials there, silver nanoparticle, gold nanoparticles, all that. It's a human made. Another one is example based on that classification, based on that type of like the structure configuration. Based on the structure configuration, you can classify it. So one is like carbon based nanomaterials. So carbon based, so basically it is a basic unit is carbon. So carbon based material, you can say that the that carbon based nanomaterials. Metal based nanomaterials, so basically if it is a metal based nanomaterials, they like in silver nano, metal oxide nanoparticle and all that. Dendrimers, if it is a dendrimers kind of a structure there, so you can say dendrimers. Composite there, if it is a composite, if more than one materials it is mixed together, and it is like chemically it is mixed, then you can say that composite, nanocomposite material. Another classification is based on the dimensions. So based on the dimension, that is basically it is a scientifically it is very useful because it matters a lot. So one is, it is a, like you can classify it into the 0 dimension material like 0D, 1D, 2D, 3D material, right? So 0D basically it is, you can say that the dimension from all sides means all three coordinates, it is a 0, means you can measure. So that you can say it is a 0D material. So means you can say all dimensions. So all three dimensions, that means it is a the electrons are confined. Okay. So this materials, it is comes under the 0D material, like quantum dots. Hello, I am audible? I am audible? Hello? Hello? I am audible?
Technical problems.
Sir, I am audible? Sir, am I audible?
Yes, sir, audible, sir.
Okay, okay, fine. Thank you. So 1D material, so one dimension material. So basically it is the dimension you can measure means it is beyond that nanometer scale. So that you can say that it is a 1D. So other two dimension, that means it comes under the nano scale. So you can say that like a nano rods. So nano rods means in one dimension it can be like beyond that nano scale level, but other two dimension it will be nano scale. So that's why like that means electrons are confined in 2 dimension 2D, but whereas the electrons free flow movement is there in the 1 dimension. So this material, it comes under the 1D material. So like nanowires, nano rods, nanotubes, all this comes under the 1D material. 2-dimensional material. So basically the 2-dimensional material. So that means the dimension, measurable dimension means it is the dimension beyond the nanoscale level. So in the two sides, so 2 coordinates it is there. But in the 1 coordinates, it is the dimension means it is a confined. The electrons are confined means the one in 1 coordinates you are having that dimension in the nanoscale level. So that is all the materials, it comes under the 2D materials like nano sheet, okay, nano films, all these materials, it comes under the 2D materials. 3D materials, where it is in all 3 dimensions you can measure it. So basically you can say that it is a building block of the nanomaterials and it form the 3D like a nanomaterials of that. Right. So these are the classifications based on the dimension, and it is people normally it refer based on the dimension. So easily like people used to try to get easily like convinced. Yeah. So these are the like you will get that properties of that. So for example, if you look it into that, their electronic behavior. So electronic behavior, as you see, when you move from the 3D to 0D, so 3D, as you see that when you plot the density of a state versus energy, so you see there is a continuous band structure there. Whereas if you move to the 2D, so there is a there, but here you are getting the steps of that. And if you move to the 1D, so that you see that the density of states at particular energy, you are getting very high. But in the further, if you move like 0D material, so you are getting that at particular energy, you are getting the high density of a state, but other energies, you are not getting any density of a states. So like that here, so as you see, there is a lot of change in that when you are moving from 3D to 0D material. So here some examples it is given, as you see that here nanotube, quantum dots, nanowires, nanocrystals, and these are all, it is a man-made material. These are whatever the example you are seeing that. So people like they used to synthesize. And as you see that here, the DNA, they are like repairing the DNA by using the fullerene on that. You can do. Coming to the another like synthesis part of that. So next part of my talk is the synthesis. So now the challenge is how to synthesize the nanomaterials of that, how to control the size of that. It is not that simple jobs to control that the size of the particle. So that means you have to get some extra effort of that. You have to put some extra effort to control the size of the particle. So here, as you see that it is basically two approaches people can apply that. One approach is that top down. So from top, you can come to the down stage, means at the nanoscale level. Another one is, it is called bottom up approach method. So bottom up means you are having that atomic scale level, that your material at the atomic scale level, and then you are bringing up, you are controlling the assembly process, and you are bringing to the nanoscale level. So these are the two approaches people follow it to synthesize the nanomaterials of that, and these are the few examples of that. So here basically I am going to like focus on the reverse micelle and that sol gel method. So reverse micelle method. So basically it is a reverse micelle method. You know that it is an example of the one. It is a microemulsion. So microemulsion, it is a very stable if you compare to the emulsion of that. So here is, you can see that this cartoon image, it is the emulsion it is showing, and this is the basically microemulsion. So what is the basically difference here? So emulsion, basically it is a mixture of two immiscible liquids, right? So basically if you apply that like mechanical energy to the two immiscible liquids, if you try to mix it, so what will happen? It will be get emulsified. So emulsified, so it will form emulsion, but the problem is here, it is unstable, and of course it is a non-transparent. So this unstable, if you keep it for the longer time, what will happen? It will be get again, it will be back to the original state. So that means the two liquid, it will be get separated. Okay, and now the thing is how to get stabilized, and this basically the emulsion. So what you can do it, you can make it to the microemulsion while making to the smaller droplets of that. So you can make smaller droplets and disperse into the another, and that smaller droplets, it gets stabilized by the using the surfactant of that. So basically the idea is, if you use the surfactant in that two immiscible liquids, so that surfactant, it is basically it is made up of the polar head group and the tail part of that, non-polar part of that. So it consists polar head group and non-polar tail part of that. So basically this part, you can say it is a hydrophobic in nature, and this part, it is a hydrophilic in nature. So hydrophilic nature, you know that it is a tendency, it loves the water molecule, whereas this part, it loves the organic molecule, means non-polar, non-aqueous solution. So when you are having the two immiscible liquids, so surfactant, it is the nature, the beauty of this molecule is it can interact with aqueous and non-aqueous solvent, both solvent it can interact. So what will happen that when you add the surfactant here, then if you just stir it, means that mechanical energy, whatever you have applied here to make the emulsion, same mechanical energy if you applied here, okay, so that means you are having A, B, and plus this surfactant S. So A, B, S, all three you are having, and you just stir it. So what will happen? One solvent, it will be get dispersed into the another solvent. So that is basically it. It depends on that the water and oil ratio. So it depends on the water and oil ratio. It will decide which one it will disperse into what, right? So if you are having the water and oil ratio is less than 1, so that means your oil proportion is more and water is less. If water in oil means water and oil ratio is greater than 1, it is a that means you are having the water proportion is more and oil is less. So that means what does mean? So basically here you can say that the water where the water and oil ratio is less than 1, so that means water is dispersed into the oil. So that's why it is called water in oil. And if the water oil ratio is greater than 1, so that means you can say the oil is dispersed into the water. So you can say oil in water. So that means water in oil and oil in water, you can say that. So water in oil means water dispersed into the oil, and oil in water means oil dispersed into the water. So in that, now once the droplet, when it is a dispersed into that, so that means it is a dispersed in the form of droplets. So when the form the droplets, so this surfactant, it cover the entire droplet surface of that. Once it is covered the entire droplet surface of that, so that the droplet surface, the nature of the droplet surface, it gets changed. Means it become from hydrophobic to hydrophilic, hydrophilic to hydrophobic in nature. So that means it can easily, like, it can be miscible. You can say that miscible, that small droplet miscible in another solvent of that. Like that, you are changing the properties of that. So that's why this entire system, it get stabilized. So the microemulsion, that's why it gets stable, and you can get the very clear transparent solution. Even put for a longer time also, it will be highly stable. So surfactant, like these are the surfactant, it is available, and you can categorize in the ionic and non-ionic and deuterionic. So ionic basically in the form of anionic and cationic. So as you see that, so these are the basically, it is a commercial name, that abbreviation it is given. So like AOT there, SDS is there, CTAB there, DD AB is there, SB316, terzitol, NP3, Triton X100. So this non-ionic surfactant, as you see that the terzitol and Triton X100, it is used. Whereas CTAB, so these are the like some common surfactants there, that CTAB, AOT, and terzitol. So people use, depends on that what kind of material people want to synthesize it. So we will see in the later slide what is the like basis for the to choose them that surfactant of that. Okay, so now what we have learned from that past slide. So basically the microemulsion, it is having the 3 components. So it is a one organic solvent, another one is aqueous phase, then you are having the surfactant. And the fourth one is co-surfactant. So co-surfactant basically you are using to further stabilize that microemulsion process. So that's why it is used, the co-surfactant of that, right? So, but basically it is a 3 component system. So, but to further stabilize, you are using the co-surfactant of that. And this, how to get it, like how much proportion it will be there. So that basically that you will get the idea from when you plot that phase diagram of that. So when you plot the phase diagram, then you can get your information, like where to what the composition you can keep it, so you can get the proper the microemulsion of that. So you can get the water in oil, or you can get the oil in water, or you can get the bicontinuous phase, or you can get the gelation. All that, it depends on that your phase diagram, you can identify it. Yeah, so I was telling about it, like what type of surfactant you can choose, and like what the structure basically will get it. So basically that it will, you can find from the surfactant packing parameters. So surfactant packing parameter, basically it will tell you, it will give an idea about it, what kind of structure basically will get it. So as you see that the surfactant packing parameter, basically it related to the volume, area, and length of that hydrophobic tail. Right. So if you put it in the equation and you can derive, so the value, whatever the value you are getting, so it will tell about it what kind of the aggregates you will get. So when you are having the spherical micelle, you are spherical micelle, when you will get, when the surfactant packing parameter is 1/3, and cylindrical micelle when you are having the half. Lambda micelle, so you will get like when it is a 1, and reverse micelle when it is a greater than 1 value, you are getting that. So now the again the point stands that how to use this the microemulsion to synthesize the nanomaterial, right? So still it is a question. Now here is the answer for that. So basically the reverse micelle, where you are having the water in oil. So water, it is inside the like core it will be there. So this is like a reverse micelle structure basically we will get. So here as you see that arrangement of the surfactant which is arranged, and inside it is form a core, and inside the core basically it is aqueous phase is there, and outside whatever it is there, it is a oil phase is there, right? So that means this droplet, whatever this droplet is there, it disperses into the oil phase, and inside what it is there, it is aqueous phase is there. So aqueous phase, whatever you want to synthesize it, you make the aqueous solution of that, and then you have to make the reverse micelle of that, right? So when you make it, then along with the dissolved aqueous solution of that, this it will go into the core. And when it is going to the core, that means you are limiting the size, you can say the reactor of that, where the reaction is taking place of that. So when you are limiting the size where the reaction is taking place of that, that means you can able to control the size of the nanoparticle of that. So basically this is the concept behind this. Okay, so basically here you have to choose the appropriate the reverse micelle. Now like surfactant, oil phase and aqueous phase, of course it is there, an appropriate salt where to dissolve into the aqueous solution, and then you mix all together, and then you can able to get it, you can able to synthesize it. This is, it will tell the further clear picture of that. So this is how to make it, that material, the nanomaterials of that. So this is like you prepare that, suppose if you want to synthesize like AB nanomaterial is there, where you are having A is one metal and B is another metal of that. So what you have to do, that you can take the precursor of A and precursor of B, and for the precursor of A you make the microemulsion 1, and for B you can prepare the microemulsion 2, right? And that you have to now mix together. After mixing together, what will happen due to the collision, that droplets it will be get like a collapse each other, and then it will be like a form a bigger like a droplets of that, where it can like it can mix the solution of that. Now at this stage, A and B, all it is a mix together, and then it react and it forms the AB size particle. So this way you can able to synthesize the nanomaterials of that. So this is like called the reverse micelle method. So this is, as I told you, it is a very, the material which doesn't, this synthesis methodology doesn't require the much like sophisticated equipment. You can make into the like in simple lab. So one of the example there, like nano cadmium sulfide. So nano cadmium sulfide, you can make it to the lab if you are having simple like a beaker, some conical flask and all that. Very simple, like you need that, and apart from that, appropriate chemicals you need that. So based on that, you can by this method you can synthesize the serious nanoparticle. Hello. Hello. Okay. How much time I have? Hello. Hello. How much time I have? Is it audible?
Hello?
Shall I continue another 10 minutes? 10 minutes, you okay? Okay, fine. Yeah. So as you see here, so with this method, so you can synthesize this the nanomaterial. So it is the process is very simple, and this you can compare with the synthesized by simple method. Just you can take the cadmium precursor and the sulfur precursor, and both you can mix both you can make it the aqueous solution of that. And when you mix that, you will find that the particle, whatever it form, it is a form the bulk particle, where the previous case it is forming the nano. So here you can easily visualize the optical change in the optical properties of that. So here you can see that the particle, it will show the yellow color, but here you can find the orange color of that. So this is the very good method you can show into the lab. So to the students can easily understand what will happen when the size it is changed to the nanoscale level. These are the few examples which is synthesized in our lab. So these are the some nanometers of that. So as you see that, so the size is some the nanometers is it's a very small, it is a 10 to 50 nanometer. Some it is it is synthesized where you are having the 50 75 nanometers of that, and some nano rods also there. So basically, if you look into the advantage of that, so as I told, so it is a main advantage is low cost equipment, but and of course it is like a very uniform size of particle you will get with that. But one, it is a drawback is there here, this, it will be like it is not environmental friendly. So because a lot of solvent, it is a wastage solvent, it will generate a lot of waste solvent, it will be generated. So that's why this is the one drawback which are people avoid to use this method. But if you chemistry point of view, if you see, it is a like with this you can easily understand how this is by using the simple method you can synthesize the nanoparticle of that. Another method, it is sol gel process. So sol gel process, it is basically it is a hydrolysis and condensation process of that. So when one is like one methodology where you are using that the metal precursor itself you are choosing in such a way that it get hydrolyzed, and that itself it is a get condensation and form the three-dimensional network of that. Like you are choose if it is a titanium isopropoxide, tantalum isopropoxide, and all that. If you choose it, or butoxide or propoxide, so these are it is a cell, it is a easily hydrolyzed, and once it is hydrolyzed, it can get condensation also. So once it is get condensation, it will form a three-dimensional network of that. And once it is like if you calcine it and center centered it, you can get that the nano size nano powders. You can get the nano. You can get the ceramics. You can get the nano fiber, nano disc. All that you can possibly able to get it. Here is the modified sol gel method. So modified basically here, if don't want to use the metal precursor of that. So metal precursor in the form of isobutoxide, isopropoxide, and all that. So what you have to do that, you can use that the polymer citric method, where the citric acid and ethylene glycol it is used as a to make the three-dimensional network. And this cavity, whatever the cavity it is formed when you are making the three-dimensional network, the cavity where it is used as a formation of the nanomaterials of that, right? So here it will be like the metal ion, it will be get into the cavity, and then it will be like slowly the reaction it will take place of that. So basically the idea is by this cavity, the size of the particle it can control. The advantage of this method is basically is a lot of variety of materials basically you can get. So like you can get from the dense film to dense like a ceramic fiber, you can able to get that, right? So dense ceramic, then aerosol, zerosol, and uniform particles, nanoparticle, you can able to get it, right? So both at that, like you can do at the metal alkoxide, from that you can process, or from the sol you can process, or when even it is forming the gel also, from the gel also it can like process, and you can get the variety of the materials you can get, right? And this also it is required not very sophisticated equipment. It is a simple like using the glasswares and some magnetic stir and all that. So with that you can able to synthesize it. So as you see, this is the lab picture. So you can able to from starting to at the end. So this is the product of that. So here basically you are dissolving. So all you are dissolving the metal precursor of that. So it is getting clear solution. Then after forming the here the gel, and gel will when it is a carbonized. So basically you are burning, and one is a carbonized, so you are getting this char powder, and finally when you are burning at high temperature, then you are getting the your final powder of that. So this is also like here you can this is the low temperature method, and not required very costly equipment. And one advantage is here, this you can scale up, right? So that's why the industry also it is uh, very much used that method. This is another like the process it is given here. You can use for the synthesis like gold nanoparticles by sol gel method. Next is here some applications. So basically in that area we are working here. So like one is water purification, where you can degrade the organic pollutant. Another one is the green and sustainable energy by generating the hydrogen as a gas, right? So through the water splitting process. So basically to this, you know that it is a at present it is a great challenge that water pollution is a great challenge for the society, and getting the green energy, right? So in that, like how this nano like it can serve the purpose of that. So basically this is this you can do by using that photocatalysis process. You can do that. So photocatalysis process, basically if you just compare with the photosynthesis, it is mimic of that, right? So photosynthesis, what you are doing, that what is happening basically, so basically the smaller molecule converted to the bigger molecule of that. So a smaller molecule, like everyone know that the carbon dioxide and water, it is joined together and form the starch. So it is a big molecule. So a small molecule joined together, it form the big molecule of that in the presence of chlorophyll and by absorbing the sunlight. So here, what we are doing that, now here it is a reverse, you can say that. So the pollutants, normally whatever the water pollutants are there, it is a bigger molecule, bigger organic molecule will be there. So that basically what we are doing, we have to, if it is a decompose into the smaller molecule like carbon dioxide and water, so water, it will go to the water body, and carbon dioxide, it will get escape from the water. So basically what you will get the pure water of that. So that is basically idea. So how to do it? This, so that you can apply the like photocatalysis. So that means here what you are doing, the bigger molecule, you are splitting into the smaller molecule of that, right? So then you are like addressing to the water pollutant. Another one is like you are doing the water splitting. So water you can split into the hydrogen and oxygen. So water, you know that it is contain the hydrogen and oxygen. So only thing is you have to appropriate energy, and you have to split into the hydrogen and oxygen. You can get the plenty of hydrogen, and which you can like it will serve the your green energy purpose. So for that, it is some like the idea how it will be, how it can done, how it can you do that. So basically the idea behind is when you are like the photosynthesis, you have used the chlorophyll. So for the photocatalysis, basically the catalyst here is play the role of that. So catalyst, which it absorb the light, and after the absorbing the light, so what happened, it is it get in the excited state. So the excited state means the electron move from valence band to the conduction band of that, right? So this, it can no, the which material can serve the purpose of that. So metal, you know that, so metal, it is because it is a continuous band is there, so metal, it cannot serve the purpose. Insulator, the energy is very high, so insulator also it cannot serve, because it has to absorb the sunlight. When you want to use the sunlight, so that means it is absorb the sunlight of that. So that means UV visible radiation. So that means insulator also it cannot work. So that means your only option is semiconducting material. So that means semiconducting material, it can serve the purpose for the photocatalysis. Okay, and this when it is going to the excited state, so it is, that means your electron is getting excited to the from valence band to conduction band, right? And what happened with that? It is basically a generating electron hole pair. So electron reside into the conduction band and hole reside in the valence band of that. So that's why it is generated electron hole pair, right? And what it happened basically, so same material, same thing is there, same molecule, basically it is creating two at two point at the conduction band. Here it can reduction process can take place, and the valence band the oxidation process can take place, right? Because here is you are having the hole, the positive charge, and here conduction band you are having the electron, that is a negative charge. Another point is like for this two, whatever the application I have, I'm going to discuss. So basically that this is like some in the material, you have to see their band is potential. So band is potential means the valence band is potential and conduction band is potential, where it is situated. So that is very important. So here it is given, for example, for the water purification, so degradation of the organic moiety. So basically what is the condition? So condition is the conduction band is potential. It should be more more negative than minus 0.33 volt at normal hydrogen electron. Whereas the valence band is potential, it should be more positive than plus 2.68 volt. So this is the requirement for the to degrade the organic moiety, organic pollutant. Whereas for the hydrogen generation, you are having the conduction band is potential should be more negative than 0 volt, whereas valence band is potential, it should be more positive than plus 1.23 volt. So if this criteria meet, then your material is suitable for the particular application of that. If doesn't match, then of course it will not take place of that, right? So this is the overall mechanism of that. So how that it can take place of that. So this is the material, and material, once it is absorbed the light, it forms the electron hole pair. Then this electron hole pair, it should migrate on the surface, because whatever the reaction is taking place, it is taking place at the surface. So this migration at the surface is very important. So here the oxidation reduction process takes place of that. But simultaneously, one disadvantage, you can say that is a recombination of the electron hole pair. Whatever it is generated, there is a simultaneously electron hole pair recombination also takes place of that. So that is, you have to minimize the recombination process, and you have to maximize the charge separation of that. So then the oxidation reduction process, it can take place maximum, right? So another thing is like people normally used to, like, lot of effort they used to put the material synthesize the visible active material, right? So you can both, you can visible and UV active material, people used to synthesize, they used to work. And fortunately UV active more materials it is there, which it serves the purpose of that, because it is like cover the valence band and conduction band is potential also, whatever the requirement is there, because that band gap is very high band gap material. But the problem is, if you want to use that artificial lamp, then it's fine, it is no problem. But if you want to use the sunlight of that, so sunlight, basically the composition of the UV radiation is very less, whereas visible radiation is very high, you are having the 45% of that. So that's why maximum that people used to put the effort to bring UV active material to the visible active material, right? So your activity get enhanced by 9 times just by tuning the band gap of the material, right? So these are the some efforts people used to do that. So to change the to modify the band gap, and to make to bring down to the UV active to visible active material, right? These are the some efforts that, and these are the some materials, as you see that there is a band gap it is mentioned, and some like valence band is and conduction band is potential also mentioned, right? So valence band is potential, you can say that it is some material it is meeting the to that specific application, right? And some it is not meeting that. So based on that, we are selecting the materials, and based on that we can making that doping, or you can compose it like that. You can play with the material, you can make the appropriate material, right? These are the some application of the photocatalysis. As you see that in a lot of sector, it is this application there. You can go from soil purification to solar cell, self-cleaning, air purification, sterilization, hydrogen energy, and deuterization, all that in water purification. Right. So few slides that some just I will cover that some application of that. Just I'm winding up. So basically here you can say that these are the pollutants, like you can say that these dyes, which are greatly used in the industry. So these are rhodamin B, and you see that this, if you treat it, this is the treated water. So as you see that here, it become very clean. It become, you can say, like a pure water. Right. So this is like a material. One material is there like a graphitic C3 and 4. So it is a very good material. It is a 2D material. It is a visual active material. And one advantage, you can say the advantage is chemically highly chemically. You can say that uh, non-reactive. You can say, and mechanical and photo. It is highly stable, right? But only the problem is here is the recombination rate, means electron hole pair recombination is very high of that. So as soon as the electron hole pair it is formed, the tendency is to again it is recombined. So that means the electron hole pair, it cannot be used for the oxidation reduction process, right? So that is the, you can say, disadvantage of that. So how to overcome this problem? So this we have make the effort here to say, to make it the nanocomposite of that. Right. So how to make the nanocomposite with what material? So another material what we have chosen the silver phosphate, and the silver phosphate, you see that it is a the another disadvantage here. If silver phosphate alone, if you synthesize, that is here is one is the poor photostability, another one is low surface area, right? And because of this also it is showing the less activity. So what we have done to make we have make the in situ composite of that, right? Nanocomposite. And when we have make the in situ composite, this material, it is very well, you can see that the silver phosphate well deposited on the graphic C3N4, right? And the activity it become very high. This, as you see that the synthesis process, so it is very simple. Like this is the graphic C3N4 seat is there. Over it, it is a deposited silver ion, and then after it is a ion exchange with that, and then it is formed silver phosphate of that. So with this method, in situ method, it is synthesized the composite, the graphitic C3N4 silver phosphate nanocomposite, and this is work like a very very active, you can say that active material. It is within 10 to 15 minutes, the whole dye it is decomposed, and we got the clean water of that. This is what we talk about the water pollution of that. Another one is like how to achieve the green energy production of that, means hydrogen generation. So hydrogen generation through the through the water splitting. So what we have done here, one example I am saying, I am not going into the detail. So just it is there, it is a tri-composite, you can say that. So here you are having the ternary composite, like a ternary, you are having the lanthanum ferrite and cadmium sulfide and carbon quantum dots. So this is the methodology, synthesis methodology, where the first is synthesize the cadmium sulfide nanorods, then on that it is deposited the lanthanum ferrite, and then after on that the carbon quantum dot it was deposited. And this with this material what we achieve nearly 25,000 micromole per hour per gram. That is the hydrogen production we got it, and still further we are trying to improve it to get the better and better hydrogen production of that. So with this I close my talk. So I acknowledge to all my students, the past and present students, all my my guide, which are always encouraged to do the some great for the scientific society, and Professor M. V. Shankar for that hydrogen evolution reaction, and my funding agency. So thank you one and all. So any question?
We
So
started with this seminar with a simple introduction and
any question?
స్టూడెంట్స్ కి ఏమైనా క్వశ్చన్స్ ఉన్నాయి అడగండి సార్ కంప్లీట్ చేసేయండి చెప్పండి సార్
sir, I'm giving you
ఆయన గురించి చెప్పు అమ్మాయి సరే
Thank the speaker. Now we move on to technical section 7. For our presentation, I would like to invite the B. Srinivasan and Professor Chemistry. I will call it a portion of science calculator. Please come to the page. I request you that our presentation to
అదే ఆయన వెళ్ళలేదు
Now I hand it over to my chairperson of this session. Thank you.
Good afternoon. Today's session of last session, technical session,
నాకు ఇక్కడ వాట్సాప్
Hello. Yeah.
సార్ కంప్లీటెడ్ సార్ మీరు డియాక్టివేట్ అయిపోండి సార్
Okay. Okay. Thank you. Thank you.
ఓకే సార్ థ్యాంక్ యూ సో మచ్ సార్
Thank you.
ఓకే సార్
So I am leaving the meeting. Okay.
నా వాట్సాప్ ఓపెన్ ప్రసాద్ గారు దాంట్లో ఉండొచ్చు ఫస్ట్ వచ్చి ప్రసాద్ గారు శ్రావణ్ గారు
Good everyone. Am I audible?
Right.
Please be quiet for some time. Good afternoon. Good afternoon. So my name is Shami. Lecture on the topic called nanomaterials and environmental patterns. Today, please be calm for 5 minutes. Okay. As a part of our today's seminar, I would like to give a presentation on nanomaterials and environmental patterns. Next slide. Next slide, please. Okay. So, as a part of our seminar, I would like to cover the topics like introduction about the nanomaterials and also the role of nanomaterials, the challenges, and the conclusion that I am going to give. Next one. Okay, now I ask you a question. How many of you know about environmental pollution? Is there anyone who can answer about environmental pollution? Are you following? What do you know about environmental pollution? I can tell some of pollution currently. Are how many types of pollutions are there? The basic types of pollution. Can anyone answer? Please, madam, stand up. How many types of pollutions are there? Little louder, please. Water pollution, air pollution, soil,
Sound.
sound pollution. Very good. Thank you. So see, we know a point that environmental pollution is a pressing challenge of 21st century, right? ఇప్పుడు మనం ఇంత సౌకర్యంగా ఏసీలో అన్ని పెట్టుకుని కూర్చున్నాం ఇక్కడ. We know that it is harmful to the environment. Don't we know? అందరికీ తెలుసు కదా environment కి pollution అని. Even though we are using that, in turn we are harming the environment. Now, what the topic is, as the population is increasing everywhere, pollution is also increasing. We need to find another way to fight these pollution. Next slide, sir. Sir, next slide, please. So environmental pollution means reduce error. In order to reduce the pollution, even though the last students, are you following? Last check. In order to protect our environment, we have to find an alternative for the pollution. Environment ni protect cheskodam kosam pollution eradicate మనం already tradition methods ద్వారా the challenges that we are facing is those are of low efficiency. That means they are not significantly reducing the pollution. And also their instrumentation cost is high. Whatever the instruments we are using to reduce the pollution, their cost is high. The third one, the secondary waste streams. They are also producing the waste products. Now, what's the alternative? In order to protect our environment, we must inform the solution. That solution that answers the question is our nanomaterials. So, nanomaterials have got a revolutionary background for addressing these limitations. Now, we look at what are nanomaterials. So, next slide. So, nanomaterials, I think from yesterday you are following this topic nanomaterials. Nanomaterials are the materials whose size is from 10⁻⁷ meters to 10⁻⁵ meters. We call it as nanoscale. Like see, whenever a normal material, the normal one is substance, when you brought it to the nano level, that is 10⁻⁵ meters, it is exhibiting an exceptional property. It is exhibiting. Those properties include the optical properties. I think you have followed the earlier session. Dr. Vijay Shankar sir explained. He said that gold material and brought to the nano level has changed color. That session winner color. Gold material మనకి nano level కి తీసుకొస్తే whatever the gold ornaments are wearing. Just look at the they are wearing gold ornaments which are of yellowish in color. But when you got that gold material to the nano level, అలాంటి gold nano level కి తీసుకొస్తే the color of the gold material got changed. This concluded that the optical properties can be altered when you bring a material to the nano level. That's the first one, optical properties. The second one, we have the electrical properties. So see, whenever a material is brought to the nano level, its conductivity will be increased. The other things, the magnetic properties will also increase, as well as the absorption capacity, reactivity, all will be increased. So my whole point in this slide is that materials at the nano level exhibit very useful properties. Next slide. So what we have discussed so far regarding the environmental pollution and introduction to the nanoparticles. Now we'll see how the nanoparticles can help us in reducing the environmental pollution. So nanoparticles మనకి pollution తగ్గించడానికి ఎలా యూస్ అవుతాయి? That's the present concept. So what does nanoparticle do is that they can identify type of pollutant by which variant of pollutant we are getting the pollution. దేని వల్ల మనకి environmental pollution జరుగుతుంది. That can be identified with the help of nanoparticles. And also the concentration of pollutants. The amount of pollutants present, those can also be identified with the help of nanoparticles. The third one, penetration into the pollutant. So the nanoparticles are very smaller in size, very micro level particles. They can easily penetrate to any of the substance. Now these nanoparticles will penetrate into the pollutant and will reduce that. Next slide. Okay. Now the types of nanomaterials. We have 4 basic types of nanomaterials which we can use for reducing the environmental pollution. Those are mainly carbon based, metal and metal oxide, silicon based, and the polymer based. We have a particular nanomaterial called the carbon nanotubes. These carbon nanotubes, as we have discussed the properties earlier, they reduce the concentration of pollutants. Now listen, environmental pollution is a pollutant concentration. Like whatever the pollutant concentration, those can be reduced with the help of the carbon nanotubes. Next one. Metal oxide, like zinc oxide, magnesium oxide, whenever nanomaterials are made with these kind of oxide, the oxides are nanometals and they are helpful in monitoring the pollutant. So the level of pollutant can be monitored with the help of this. Next one. So till now what we have discussed is that nanomaterials are effective in reducing the pollution. How it can reduce that? By deploying the sensors, namely these electrochemical sensors, optical and FPD sensors. Is there anyone who can give me the abbreviation for FPD? FPD and the full form of the any student identify it? Know the abbreviation of FPD sensor? FPD sensor performance. Is there anyone? Any other student? Whatever is called. FPD stands for the field effect transistor. FPD sensor. So whenever the nanomaterials are brought from field effect transistor sensors, they are useful in reducing the pollution. Next one. Okay. So we know that we have learned till now nanomaterials can help us in combating the environmental pollution. In this process, there are some challenges that we need to fix. Those include the technical and the economical challenges. Like there are issues called cost productive. We like minimal money to even achieve. That's one of the challenges. And from the technical to the laboratory session into practical session to these products, there are also challenges. Last bit, environmental impact. Is it suitable for the environment or not? Environment is eco-friendly or carbon we need to cross it. Last one, the conclusion, directly for 2 minutes I'll conclude this. So whatever we have learned so far, environmental pollution is a challenge that we need to fight with. Even though the traditional methods have failed, we got a new solution for the nanomaterials. Due to the versatile properties, we can employ nanomaterials in fighting with the environmental pollution. Okay, thank you.
Next presentation, K2BS Nature, third BSc, PR College. Topic Engineering Nanosphere Functionality.
సార్ బీపీటీ అకౌంట్ పేరు సాయా సాయా డౌన్లోడ్
Good afternoon, everyone. My name is Convergence from PR Company College. Today, my topic is engineering and nanoscale functionalities. That is it. Slide. Introduction. This presentation will explore the more fundamental principles and ecological uses and designs and applications of advanced functionalities and nanomaterials. We will develop into synthetic methods and characterizations, techniques and scientifications of these materials in various ways. We have to see the synthetic methods or manufacturing methods or designs of nanomaterials, and we have to check the characteristics of nanomaterials and synthesis of methods of manufacturing methods. Here, nanomaterials are synthesized through various methods, including top to bottom, top to down, and bottom to up. Nanomaterials are design చేసుకునే top to down and bottom to up. Nanomaterials in the design top to down on divide చేసుకుంటాం దాన్ని ఫ్రేగ్మెంట్స్ కి అంటే నానో మెటీరియల్ సైజ్ దాన్ని తీసుకోవచ్చు అండ్ బాటమ్ టు టాప్ అంటే ఆటమ్ సైజ్ నుంచి క్రిస్టల్ సైజ్ వరకు తీసుకుంటాం అంటే మనం ఆటమ్ సైజ్ అనేది మనం 10 to the minus 12 దాకా ఉంటే దాన్ని మనం 10 to the minus 9 10 to the minus 7 to 10 to the minus 9 వరకు తీసుకోవచ్చు దాన్ని నానో స్కేల్ స్ట్రక్చర్ అంటే నానో స్కేల్ స్ట్రక్చర్ అంటే 10 to the minus 7 to 10 to the minus 9 వరకు ఉంటుంది క్యారెక్టరైజేషన్ అండ్ టెక్నిక్స్ అంటే ఇప్పుడు మనం నానో మెటీరియల్స్ అనేది తయారు చేస్తున్న దాని యొక్క క్యారెక్టరిస్టిక్స్ అనేవి ఎలా ఉంటాయి ఎలా చెక్ చేయాలనేది కొన్ని మెథడ్స్ అని యూస్ చేసి దాని ప్యూరిఫికేషన్స్ అండ్ డ్రగ్ కంటెంట్ అండ్ సైజ్ డిస్ట్రిబ్యూషన్ చార్ట్ అవన్నీ షేప్స్ అని ఈ టెక్నిక్స్ అనేవి యూస్ చేసి మనం చేస్తారు some of the techniques is scanning electron microscope and transmission electron microscope and atomic force microscopes or etc. We have the microscope used to characterization of atomic nanomaterials. Challenges. We have to see the challenges of nanomaterials. We have to prepare the characterization side and తర్వాత మనం challenges అనేవి ఫేస్ చేయాలి ఏ challenges అనేవి ఫేస్ చేసుకుంటామంటే దాని యొక్క క్వాంటిటీ కంట్రోల్ అంటే ఒక నానో మెటీరియల్స్ అనేది డిజైన్ చేసిన తర్వాత దాని ప్రాపర్టీస్ అనేవి చేంజ్ అయిపోతాం ఆ చేంజ్ అవ్వకుండా చూసుకోవాలి అండ్ మెయింటైనింగ్ ది కాస్ట్ ప్రొడక్షన్ ఆఫ్ కాస్ట్ దాని యొక్క కాస్ట్ అనేది చెక్ చేసుకోవడం అండ్ ఎన్ష్యూరింగ్ రీప్రొడక్టివిటీ దాన్ని మళ్ళీ మనం యూజ్ చేసేలా చూసుకోవడం అండ్ తయారు చేసిన దాన్ని మనం ఎకో ఫ్రెండ్లీగా కాదని చెప్తాం అప్లికేషన్స్ ఎనర్జీ స్టోరేజ్ ప్రిపేర్ చేసిన దాంట్లో ఇందాక చెప్పాను కదా సర్ఫేస్ చార్జ్ అండ్ డ్రగ్ కాంటెంట్ ఇలా నెంబర్ ఆఫ్ ఉంటాయి దాంట్లో మనకి ఎనర్జీ స్టోరేజ్ లో దీని హ్యాస్ హై conductivity ఉంటుంది దీని హ్యాస్ హై సర్ఫేస్ అండ్ some batteries are used for storing this type of energy. Lithium sulfur and lithium ion batteries are used to increase the cycle of the life and reduce the charge time. And మనం లిథియం అండ్ సల్ఫర్ అని యూజ్ చేసినప్పుడు దాని చార్జ్ టైమింగ్ అనేది మనకి చాలా తక్కువ ఉంటుంది అంటే ఛార్జింగ్ తీసుకోవడం అనేది చాలా తక్కువ ఉంటుంది లైఫ్ సైకిల్ అనేది చాలా ఎక్కువ ఉంటుంది బయోమెడికల్ లో నానోమెటీరియల్స్ అనేది ఎలా యూజ్ చేస్తారంటే in the biomedical engineering nanomaterials are utilized for targeted drug delivery and imaging targeted drug delivery అంటే మనకి ఏదైనా అటాక్ వచ్చినప్పుడు టాబ్లెట్ అనేది వేసుకుంటాం ఆ టాబ్లెట్ అనేది స్టమక్ లోకి వెళ్తుంది కానీ డైరెక్ట్ కంటికి వెళ్ళదు కాదు దాని నుంచి టార్గెట్ డెలివరీ అనేది యూజ్ చేస్తారు ఎప్పుడైతే మనం టాబ్లెట్ అనేది వేసుకున్నామో ఆ టాబ్లెట్ పవర్ కంటికి వెళ్తుంది లేకపోతే మోకాలకి చేతులకి వెళ్ళదు అక్కడ టార్గెట్ డెలివరీ అనే టెక్నిక్ యూజ్ చేసి ఆ టాబ్లెట్ పవర్ అనేది ఎక్కడికి వెళ్ళాలని యూజ్ చేస్తారు అండ్ ఇమాజిన్ సిటీ స్కాన్ అండ్ MRI స్కాన్ సిటీ స్కాన్ MRI స్కాన్స్ అనేది ఒక పర్సన్ కి 1 or 3 అంతే అంతకు మించి ఎక్కువ చేసుకోవడం వల్ల సైడ్ ఎఫెక్ట్స్ వస్తాయి నానో మెటీరియల్స్ అనేది యూజ్ చేసి మనం బాడీ అనేది స్కాన్ చేస్తాం అలాగంటే రోబోటిక్ క్యాప్సూల్స్ we have to use to identify the problems in our bodies. Electronics, nanomaterials in involving field. The nanomaterials are analyzed for develop the smaller, faster, and more efficiently electronic devices. This include transistors and memory chips and flexible electronics. The integration of nanotechnology of electronics paved the way of advanced in consumer advanced computing. Nanomaterials అనేది యూజ్ చేసి మనం ఫాస్ట్ గా గ్రో అవ్వడానికి ఎలక్ట్రానిక్స్ డివైసెస్ తయారు చేయడం ఎగ్జాంపుల్ మెమరీ కార్డ్స్ ని స్మాల్ సైజ్ లో తీసుకురావడం అలా ఎలక్ట్రానిక్స్ డివైసెస్ ని కన్స్యూమర్ ఎలక్ట్రానిక్స్ కన్స్యూమర్ ఎలక్ట్రానిక్స్ అంటే బేసిస్ ఇవన్నీ కన్స్యూమర్ ఎలక్ట్రానిక్స్ దానికి కూడా మన సైజ్ తగ్గించి ఇంకా ఎలా డెవలప్ చేయాలనేది చూస్తుంది. Conclusion. Due to the versatile properties of nanomaterials, they have two applications of different fields, ranging up for help to manufacturing electronic devices. And nanomaterials అనేది మన health to electronics devices వరకు ప్రతి దగ్గర మనం nanomaterials అనేది యూజ్ చేస్తూ ఉంటాం. That's enough. Thank you to all.
Presentation C.H. Ganga Bhavani and P. Mangalakshmi, Ideal College. Topic: Synthesis characterization of nanomaterials.
Very good afternoon to one and all present here. I am from Ideal College, and I am presenting nanotechnology, synthesis and characterization of nanomaterials for application in cost-effective electrochemical devices. The study of nanomaterials have great significant addition as a remarkable class of materials. Due to nanomaterials, their unique properties and the fact that they encompass a wide range of samples, with at least one dimension ranging from 1 to 100 nanometers. The elegant design of nanoparticles enable the achievement of extremely large surface areas. The development of co-effective electrochemical devices is very crucial for efficient energy of nanomaterials. Conversion, which is essential for sustainable development. Now, application of nanomaterials in electrochemical devices. The topic of my study: metal oxides and hydroxides, including titanium dioxide, zinc oxide, and iron oxide, have also shown promise in electrochemical devices. Nanotechnology based electrochemical sensors and characterization of nanomaterials have opened opportunities for the development of more effective electrochemical biosensors. Now, to come to nanostructure materials for analyzing electrochemical performance in energy storage devices. The interaction between the electrode and electrolyte interface significantly impacts the performance of electrochemical devices. A well-designed interface with good electrolyte compatibility minimize interface resistance and effective transfer enhance the device's overall performance beyond. Now, hybrid materials, which combine more classes to nanomaterials, have also been investigated and after the potential for improved performance and functionality.
Processor
Potential to revolutionize various fields, including healthcare, environment monitoring, and food safety. Now, I can explain the advanced functional nanomaterials. Hello, good afternoon to all. My name is Kakavani, studying MSc Second year. We met in the advanced functional nanomaterials. Functional nanomaterials. These materials possess specific functionalities such as electrical, optical, mechanical, making them essential, valuable for applications in electronics, energy storage, medicine, and environmental remediation. Classification of design principle of advanced functional nanomaterials. First, size and shape control. Determine optical, electrical, and mechanical properties. Hybrid and composite structure. Combined materials are multifunctionality. Self-assembly and nano engineering. Enable precise structural organization. Applications of advanced functional nanomaterials. Some main applications of advanced functional nanomaterials. Energy storage and convergence. Nanomaterial enhances batteries, supercapacitors, solar cells, fuel cells for improved efficiency. Environmental sustainability. Nanomaterials support water purification, air pollution control, and waste remediation. Biomedical and healthcare. Enable targeted drug delivery, biosensors, diagnostics, and tissue engineering. Advanced coatings and smart materials. Nanotechnology provides self-sealing, anti-corrosion, and responsive materials. Aerospace and automotive. Nanomaterials improve lightweight, high-strength materials and thermal management. And the last conclusion. The design principle of advanced functional nanomaterials include size control, surface functionalization, and hybrid structure. Play a crucial role in balanced properties for specific applications. These nanomaterials have transformed multiple industries, enhances energy efficiency, healthcare solutions, environmental sustainability, and advanced nanomaterials. Thank you for this giving opportunity.
Next, yeah, Vilas Reddy and B. Paul Samarkand, BSc, PR College, Nanotechnology.
Mobile.
I have got very good afternoon, Ananda. I am Vilas Reddy. I am from the PR Government College. And my today national seminar, this topic we can explain about the nanotechnology of nanomaterial. First of all, slide. Introduction to the this presentation explores the innovative use of nanomaterials in environmental remediation. And in presentation, nanomaterials మన environmental యొక్క remediation లో అంటే వాతావరణం ఎలా పనికొస్తున్నాయి nanomaterials అనేది ఇక్కడ చెప్పాలి. Types of nanomaterials. Nanomaterials can be categorized into various types based on their characteristics and structures. Nanomaterials అనేది వాటి characteristics మరియు structures ద్వారా విడదీశారు. ఈ characteristics include nanoparticles, nanofibers and nanotubes. ఇందులో మెయిన్ గా nanoparticles అని nanofibers అని nanocells అని ప్రతి ఒక్క పార్టికల్ ప్రతి ఒక్క పార్టికల్ ఒక యూనిక్ ప్రాపర్టీస్ కలిగి ఉంటుంది. And applications in environmental science. మన సైన్స్ లో కూడా అప్లికేషన్స్ అనేది దానికి types of nano properties of nanomaterials. Nanomaterials exhibit distinctive properties such as height, surface to area ratio. అంటే ఉదాహరణకు ఉపరితలం పిచ్చి reactivity and unique optical characteristics. These properties enable to them interact with the effectively with various contaminants అంటే విషపు contaminants తోనే త్వరగా ఇంటరాక్ట్ అవ్వడానికి మన నానోమీటర్స్ అనేది బాగా ఉపయోగపడుతుంది. అప్లికేషన్స్ ఇన్ రెమిడియేషన్ వాతావరణం అదే వాతావరణం అప్లికేషన్ నానోమెటీరియల్స్ ఆర్ ఇంక్రీజింగ్ యూటిలైజ్డ్ ఇన్ ఎన్విరాన్మెంటల్ రెమిడియేషన్ టు రిమూవ్ పొల్యూటెంట్స్ ని తగ్గించడానికి మన నానోమెటీరియల్స్ యూజ్ చేస్తాం. ముఖ్యంగా సాయిల్ పొల్యూటెంట్ ఫ్రమ్ సాయిల్ వాటర్ నుంచి సాయిల్ పొల్యూటెంట్స్ ని వేరు చేయడానికి నానోమెటీరియల్స్ అనేది చాలా ఉపయోగపడుతుంది. The small size and the large surface enhance the ability to interact with the contaminant. చిన్నగా ఉండడం మరియు చిన్నగా మరియు పెద్దగా ఉండడం వల్ల దాని ఎబిలిటీ వల్ల ఇంపాక్ట్ అవ్వడానికి చాలా త్వరగా అవకాశం ఉంది. Facilitating the process such as absorption, catalysis and destruction of harmful substances. Applications include the treatment of heavy metals, organic pollutants and contaminants, which are critical for restoring contaminated forest areas. ఇది మన వాతావరణంలో చాలా ఉపయోగకరంగా పనిచేస్తుంది. మై ఫ్రెండ్ పవర్ ఇది రకమైన అనుకుంటాం.
My name is Deepan Sarma. I am studying BSc Physics at Nanomaerials Degree College. Today I am here to share some knowledge about environmental radiation. Environmental radiation అంటే మన ఎన్విరాన్మెంట్ లో ఉండే వాటర్ కానీ లేకపోతే సాయిల్ కానీ లేకపోతే ఎయిర్ కానీ వాటిని పాడైపోయిన పొల్యూషన్ పట్టి ఉంటాయి దానికి పొల్యూషన్ మనం ఇప్పుడు డైలీ మనం చేస్తున్న పని వల్ల మన జీవనంలో వాటికి మన ద్వారా పొల్యూషన్ అనేది పెరుగుతుంది. దానివల్ల ఏమవుతుందంటే ఆ పొల్యూషన్స్ ని నివారించడానికి నానోమెటీరియల్స్ అనేవి బాగా యూజ్ పడతాయి. టెక్నిక్స్ ఫర్ రెమిడియేషన్. Various techniques incorporate nanomaterials for environmental remediation. This includes nanostructured filters for water purification, bioremediation methods illuminated by nanoparticles and utilizing nanomaterials to promote plant uptake of pollutants. Each technique is tailored to specific type of contamination and environmental context, leading to varying the degrees of effectiveness based on pollutant levels. ఈ రెమిడియేషన్ నానో పార్టికల్స్ జరుగుతాయని చెప్పాను కదా, ఇందులో చాలా టైప్స్ ఉన్నాయి. ఫస్ట్ చూసుకున్నట్లయితే ఇప్పుడు సాయిల్ చాలా చాలా టైప్ ఆఫ్ చాలా రీతిలో మనం ఆ సాయిల్ అనేది పొల్యూషన్ అయిపోయిన చూస్తాం. అందులో మనం నానో పార్టికల్స్ అంటే ఐరన్ అంటే 0 ఇచ్చినప్పుడు ఏమవుతుందంటే దాని ద్వారా నానో పార్టికల్స్ అందులో ఉన్న ఆ చెడు ఆ పొల్యూషన్ అంతనే ఆ సాయిల్ పెంచడానికి బాగా ఉపయోగపడుతుంది. దీనికి చాలా మెథడ్స్ ఉన్నాయి కానీ ఈ నానో మెటీరియల్ అనే పార్టికల్ ద్వారా చేస్తే ఏమవుతుందంటే ఈ నానో మెటీరియల్స్ అనేవి సైజ్ లో చిన్నగా ఉంటాయి కానీ ఈ క్లిప్షన్స్ అనేది చాలా నీట్ గా ఉంటుంది అనమాట. అంటే ఇప్పుడు మనం మిగతా మెథడ్స్ తో పోలిస్తే ఈ మెథడ్ అనేది ఇంకా మొత్తానికి దాంట్లో పొల్యూషన్స్ అనేవి లేకుండా ఉంటది అనమాట. నెక్స్ట్ చూసుకుంటే ఇంట్లో సాయిల్ చేసిన తర్వాత వాటర్ ట్రీట్మెంట్. ఏంటంటే ఇప్పుడు నానో జీరో నెక్స్ట్ ఏమో టైటానియం డైఆక్సైడ్ నెక్స్ట్ ఏమో వల్ల ఏమవుతుందంటే ఆ వాటర్ వల్ల మొత్తం పొల్యూషన్ అంతా పోయి ఆ వాటర్ ప్యూరిఫై అవ్వడానికి అది హెల్ప్ అవుతుంది అనమాట. నెక్స్ట్ చూసుకున్నట్లయితే ఇప్పుడు ఫారెస్ట్ లో కదా అదే మొక్కల దగ్గర కానీ నీరు దగ్గర కానీ సాయిల్ దగ్గర కానీ వీటిలో కూడా ఇది నానో మెటీరియల్స్ అనేది క్రూషియల్ రోల్ ప్లే చేస్తుంది. ఇంతే కాకుండా మనం చాలా రీతిలో వాటర్ లో అనేది ఇప్పుడు సీడ్స్ లో కదా ఆయిల్ ట్యాంకర్స్ వెళ్తున్నప్పుడు ఏమవుతుందంటే ఈ మధ్యలో చాలా వెళ్ళిపోతాయి. అది డ్యామేజ్ అవడం వల్ల ఆయిల్ అనేది వాటర్ తో కలిసిపోయినప్పుడు లోపల ఆర్గానిజమ్స్ చాలా చచ్చిపోతాయి. అంటే ఫిషెస్ కానీ లేకపోతే మిగతానికి కూడా జంతువులు చచ్చిపోతాయి. అవి క్లీన్ చేయడానికి కూడా ఈ నానోమెటీరియల్స్ టైటానియం ఆక్సైడ్ అటువంటి లేకపోతే కార్బన్ నానో ఇవి కూడా ఉపయోగపడతాయి వాటిని తగ్గించడానికి. Challenges and limitations. Despite the pharmaceutical limitations of nanomaterials in environmental condition, several challenges exist. So, challenges include potential toxicity of nanomaterials to non-target organisms, environmental resistance, and the uncertainty surrounding the long-term effect in the natural ecosystem. Additionally, regulatory frameworks and public perception pose significant hurdles for the widespread adoption of these technologies in forestry centric remediation projects. అంటే ఈ remediation అనే దాంట్లో చాలా చాలా ఉన్నాయి. ఇప్పుడు లిమిటేషన్స్ కూడా చాలా ఉన్నాయి. ఏంటంటే ఇప్పుడు దాకా మనకి అడ్వాంటేజెస్ మాత్రమే తెలిసి వీటికి కొన్ని డిసడ్వాంటేజెస్ కూడా ఉన్నాయి. కానీ వాటిని ఇంకా రీసెర్చర్స్ అనే వాళ్ళు ఇంకా కనిపెడతారు అన్నమాట. అంటే ఇప్పుడు దానివల్ల నానోమెటీరియల్స్ మనకి అడ్వాంటేజెస్ కాకుండా ఎన్విరాన్మెంట్ అయినా మనకైనా కూడా డిసడ్వాంటేజెస్ ఉన్నాయి. ఈ నానోమెటీరియల్స్ ఈ రోజు చాలా అంటే దీనిలో ఉపయోగిస్తున్నారు. ముందు నానోమెటీరియల్ అంటే ఎవరికి తెలియదు. కానీ ఈ రోజు నానోమెటీరియల్ ని మనం డైలీ వాడే కాస్మెటిక్స్ అంటే సన్ స్క్రీన్ లేకపోతే ఫేస్ వాష్ అలాంటి వాటిలో కానీ లేకపోతే మనం తీసుకునే బ్యాగ్స్ వాటిల్లో కూడా వాటర్ రెసిస్టెన్స్ కోసం వాటిని వాడతారు. అలాగే మనం ఇంకా ఈ నానో పార్టికల్స్ చాలా వాటికి వాడతాం. కానీ మనం ఇంకా ఈ ఎన్విరాన్మెంటల్ లిమిటేషన్ మాత్రం ఈ నానో పార్టికల్ ఒక విధంగా మనకి వెళ్ళిపోతుంది. అది కానీ లేకపోతే మనం ఎన్విరాన్మెంటల్ లిమిటేషన్ ద్వారా మనకి మొత్తం పొల్యూషన్ పెరిగిపోయి మనకే అనారోగ్యాలు మనకే సైడ్ ఎఫెక్ట్స్ ఎక్కువ ఉంటాయి. కానీ ఈ నానో పార్టికల్ ద్వారా ఎన్విరాన్మెంటల్ లిమిటేషన్ పూర్తిగా తొలగించడానికి అది మనకు సహాయపడి ఈ రోజు మనకి ఇలాగా నానో పార్టికల్ సహాయపడింది. థ్యాంక్ యూ.
Next, M. Amrutashri, third PhD, PR College. Topic: Digital Nanoscience.
Very good evening, everyone. My name is Amrutashri. I'm studying third BSc Biotechnology from PR Government College. Today, we are going to discuss about the topic digital nanoscience, advancing nanomaterial innovation through computational modeling. So, introduction to nanoscience and nanotechnology. The field of nanomaterials has revolutionized numerous scientific and technological domains, from medicine and electronics to energy and environmental mitigation. The unique properties of nanomaterials, which often differ dramatically from their bulk counterparts, arise from contaminant effects, increased surface to volume ratios, the distinct structural arrangements in the nanosphere. Understanding and predicting these properties before synthesis represents a significant challenge that has increasingly been addressed through computational modeling. Nanotechnology plays a crucial role in various scientific and practical applications, including healthcare, agriculture, transportation, environmental protection, energy, and aerospace. However, experimental studies in nanoscience face limitations due to cost, slow process, and difficulty of conducting and controlling experiments. This is where computational modeling becomes invaluable. Computational modeling and simulation of nanomaterials strongly complement physical experiments. They enable the prediction of characteristics and process under conditions difficult to replicate or achieve in a laboratory setting. The advantages include interpretation of physical measurements, providing deeper insights into nanoscale phenomena. Nanoscale dimensions. Nanoscale examines matter at 1 to 100 nanometer scale, where quantum effects dominate. Unique properties. Materials exhibit novel optical, electronic, and mechanical behaviors at nanoscale dimensions. Complex interactions. Nanoscale systems present challenges in predicting and controlling atomic interactions. The role of computational modeling in nanoscience. Theory experiment bridge. Computational models connect theoretical predictors with experimental observations. Predictive designs. Digital models enable rational design of nanomaterials with targeted properties. Accelerated development. Simultaneously significantly reduce time and resources needed for nanomaterial innovation. Key computational techniques in nanoscience. Molecular dynamics. Simultaneous atomic motion over time using Newtonian physics to reveal nanomaterial behavior. Monte Carlo methods. Statistical sampling techniques for exploring potential energy landscapes of nano-complex materials. Density functional theory. Quantum mechanical approach to calculating electronic structure and properties of nanostructures. Machine learning approaches. Data-driven models that accelerate discovery by predicting properties from existing data sets. Density functional theory application. At the foundation of computational nanoscience lies density functional theory, which has become the method of choice for predicting electronic, optical, magnetic, and structural properties of nanomaterials. Modern density functional theory, which is based on the first principles, is capable of predicting material properties and has now become an indispensable tool for material scientists. Matured and is now considered indispensable in the modeling toolbox of physics, chemists, material scientists, and engineers. DMP calculations have been successfully applied to predict various properties of nanomaterials. Case study. Nanoparticle designed for drug delivery. Interaction analysis. Computational prediction of drug nanoparticles, binding mechanisms, and stability. Parameter optimization. Turning nanoparticle size, shape, and surface properties for targeted therapy. Biological simulation. Modeling nanoparticle behavior in complex biological environment. Efficacy verification. Validating computational predicts against experimental outcomes. So nanoparticle design అనేది drug delivery గురించి కోసం కూడా వాడతారు. Interaction analysis. Computational prediction of drug nanoparticle binding mechanisms and stability. ఈ computational prediction ద్వారా drug nanomaterial binding mechanism and stability గురించి తెలుసుకుంటాం మనం. Parameter optimization. Turning nanoparticle size, shape, and surface properties for targeted delivery. Targeted delivery ఏదైతే ఉందో దానికి సంబంధించిన రిసెప్టర్ సైజ్ షేప్ ని కూడా ఈ ప్రాసెస్ ద్వారా మనం యూజ్ చేసుకోవచ్చు. Biological simulation. Modeling nanoparticle behavior in complex biological environments. Advancing nanomaterials for energy applications. Solar nanomaterials. Computational design of quantum dots and nanostructures for enhanced photovoltaic efficiency. Energy storage. Modeling novel electrode nanomaterials to improve battery capacity and charging rates. Catalysis. Simulating nanoscale catalysts for renewable energy applications and fuel cells. ఈ nanomaterials అనేవి energy applications గురించి కూడా మనం యూజ్ చేస్తాం. లైక్ ఛార్జింగ్ అలాగే ఫ్యూయల్ సెల్స్ అనే వాడతాం. దాని గురించి కూడా ఈ నానో టెక్నాలజీ అనేది ఉపయోగపడుతుంది. Nano electronics and quantum computing. Quantum structure. Simulation of quantum dots, wells, and nanotubes for electronic applications. Nanoscale devices. Modeling electronic properties of transistors and memory at nanoscale dimensions. Quantum computing. Design of qubits and quantum fields using advanced computational methods. Post-field development for nanomaterials. The accuracy of MD simulations depends critically on the quality of the force fields used to describe atomic interactions. Interatomic potential-based approaches aim to express the total energy of a connection of atoms directly in terms of their position through analytic tabulated functions. Developing appropriate force fields for nanomaterials remains challenging due to unique environments at the nanoscale. Accuracy cost balance. Finding optimal trade-offs between computational precision and resource requirement. Multi-scale modeling, bridging atomic, mesoscopic, and macroscopic scales in unified simulations. Experimental validation, verifying communication predictions against real-world experimental measures. Data-driven discovery. AI systems analyzing vast materials data bases to identify promising nanomaterial candidates. AI enhanced simulation, machine learning, accelerating, and traditional simulations by the order of magnitude. Integrated workflows, high throughput computing combined with AI for autonomous materials discovery. Impulse design, using AI to work backward from design properties to optimal nanostructures. Application in nanomaterial design, energy materials. Computational modeling has proven particularly valuable for designing nanomaterials for energy applications. The Open Quantum Materials Database (OQMD) has been applied to various materials problems, including LI battery combination catalyst Li-ion battery anodes and Li-ion battery cathode coatings received with HF. These applications demonstrate how computational models can accelerate the development of next generation energy storage technologies, nanostructure category, electronic and optical properties. Conclusion. At last, I would like to conclude by saying computational modeling has transformed nanomaterial science by enabling predictions of properties and behaviors before synthesis, accelerating discovery and reducing experimental costs. From quantum mechanical methods that capture electronic and optical properties to molecular dynamic simulations that reveal structural and thermal behaviors, the computational toolbox for nanoscience continues to expand in capability and accessibility. The integration of methods across scale from quantum to container provides a comprehensive framework for understanding nanomaterial behavior. Computational modeling enhances nanotechnology applications by predicting nanoparticle behavior and nanodevice performance, crucial for scientific and advances. By continuing to advance computational approaches for nanomaterials, researchers will accelerate innovation across energy, medicine, electronics, and environmental applications. As computational methods become increasingly accurate and accessible, they will play an even more central role in the design and discovery of next generation nanomaterials with tailored properties for specific applications. Thank you for giving me this opportunity.
Next, P. Adilakshmi, first PhD Pharmaceutical Chemistry, Digital Nanoscience, and R. Sahiti, PR College.
A very good evening to one and all. My name is Sakshi from I'm from PR College. Today I would like to tell about digital nanoscience, advanced nanometer innovation through computational modeling. So, what is nanoscience? Nanoscience is a branch of science. It deals about nanoparticles. What are nanoparticles? Nanoparticles are naked. They are not visible to our naked eye. They are microscopic level, which ranges between 10 to the power of 7 to 10 to the power of 9. So this is the range. Why nowadays nanoscience is developing very vigorously? Because nanoparticles have an ability it has flexible properties. We can change it anyways. So that is the reason we have to use nanoparticle. What is the importance of this topic? Mainly in this theme, we have to discuss about nanostructure level. Structure. What is the importance of nanoparticle structure? Okay, she can read the entire slide. In that, I will pick up some importance. Okay, important points now I discuss. Okay, next move on to the slide. The first introduction. Nanoscience dimension in ranges. Main interaction. Complex interaction. How nanoscience works because of the structure of work and its interaction On that basis, the nanostructure works. So move on to lawsuit. A second, yes, this is the structure, first nanostructure, graphite. It is a 2D particle, and another particle, I said, it is a three-dimensional particle called rock-finished fullerene. This is the first discovery in nanoscience by physical professor Patrick Charles. He was an American. At 1940, 1959. So, what is the importance of nanostructure? This is a graphite 2D dimensional structure. It has many properties. I will tell already it has flexible ranges. What are its properties? It has an optically transparent. We know our pencil works writing it will made of graphite. If you write dark and later, there is vapor like blackish color is powder that is nothing but layers of graphite. Graphite is mainly used in very diverse fields like spaces, and not only spaces in mobile. We know there are several kinds of generation in computers, but nowadays the computer science will still very low. It will consider our mobile phone screens, and this graphite is also used in observation in solar panels. What happened? Can I give an example? This is an example. If you take this is spinning something like ball. If one ball is but if you use the sizes of these spheres, what happened? Like small, that spheres. My hand has so much of sphere balls. So if you reduce the size of any particle, it has a great ability to increase the efficiency. Like that gives, if we reduce the size of the particle size, it increases the efficiency. That is the importance. So so I'm not taking much more time, so I'm complete very fast. We should learn efficiency nanoscience. In nanoscience, this is new technology development in nanoscience. We have an example, nanobots. Are you listening about nanobots? Nanobots is widely used in cancer treatment nowadays. We use treatment. But scientific research, what is the effect of chemotherapy? It has good quality size of RBC. So by using the nanobot with AI, it has an analyzing capacity to what dangerous substances, and it also you mentioned the drug delivery to targeted molecule, and it disrupts the of cancer. We are using nanoscience along with AI. This is one of the kind of example, and not only manufacturers like battlefields. We know it is very important. Battlefields also nanotechnology with the AI, along with AI, we are using what drones are. We are in drones consist of nanotechnology along with AI. It goes and like enemy spot and give signals to besides, what happened that this is, if we launch this and we go directly target, this is main application we are using battlefield and nanotechnology. It is very efficient. So that is what we are supposed to be like in the world. Good evening, everyone, and respected teachers and my dear brothers and sisters. My name is Sarah. I'm studying first BSc Honors Pharmaceutical Chemistry at Nagpur Government College, Nanomaerials. Now we are nanoscience nowadays and technology, nanotechnology. ఇందాక నుంచి చెప్తున్నారు నానో టెక్నాలజీ ఏంటి, నానో సైన్స్ అంటే ఏంటి, ఏంటి, బట్ ఎలా యూజ్ చేస్తున్నారు, ఎలా దాన్ని అడ్వాంటేజెస్ ఏంటి, దాన్ని ఎలా డెవలప్ చేశారు అని ఎవరు చెప్పట్లేదు. సో దాని గురించి చెప్పబోతున్నాను. నానో సైన్స్ అండ్ నానో టెక్నాలజీ ఆర్ యూజ్డ్ ఇన్ కంప్యూటర్స్, మెడిసిన్స్ and antimicrobial and antibacterial coating for mouse and keyboard. The study of manipulating and the initiating of matter structure monitor scales. Nanotransistors, which are transistors down to the nanometers level, average nanoscience that achieve smaller size, faster speed, and higher energy efficiency. So, 19th century లో కంప్యూటర్ అనేది వచ్చి 19th century లో డెవలప్ చేశారు. కంప్యూటర్ అనేది తీసుకొచ్చారు. దాని ట్రాన్సిస్టర్ సైజ్ ఒకటి చాలా పెద్దగా ఉండేది. ఒక ఈ రూమ్ నిండిపోయినంత ఉంటుంది. అది 800 ట్రాన్సిస్టర్స్ ఉంటుంది. బట్ ఇప్పుడు 6 crores ఉన్న ట్రాన్సిస్టర్ యూజ్ చేస్తున్నాం. లైక్ మన ఫోన్ తీసుకోండి, మన ఫోన్ లో ఇంతే ఉంటుంది ట్రాన్సిస్టర్. కానీ దాని ట్రాన్సిస్టర్ లో ఉండే పార్టికల్స్ మాత్రం 8 crores. దాని వల్ల స్పీడ్ పెరుగుతుంది, ఇంటర్నెట్ యాక్సెస్ ఫాస్ట్ గా వస్తుంది, ల్యాప్టాప్ సిస్టమ్స్ వాటి వల్ల మనకి ఫాస్ట్ ఇంటర్నెట్ వస్తుంది. మనకి కావాల్సిన ఫాస్ట్ వస్తుంది. సైన్స్ లో అలా అయితే మెడిసిన్ లో నానో సైన్స్ అనేది ఎలా యూజ్ అవుతుంది పద్ధతి ఉంటే ఏదైనా చాలా మంది పాడేవారు. లైక్ బాడీని కట్ చేసి అలా చేసేవారు. ఇప్పుడు అయితే మిషన్స్ వచ్చి ఆపరేషన్ చేయకుండానే బాడీ కట్ చేయకుండానే మనకున్న జబ్బుని క్యూర్ చేస్తున్నారు. ఒక మెడిసిన్ లైక్ మన బాడీలో ఏముంది అని చెప్పి పిల్ క్యామ్ అది క్యాప్సూల్ లా ఉంటుంది. దాన్ని తీసుకున్న వెంటనే అది మన బాడీలోకి వెళ్ళి బ్లడ్ సర్క్యులేషన్ లో కలిసిపోయి మన బాడీలో ఎక్కడైతే డ్యామేజ్ ఉందో, ఏ పార్ట్ లో అయితే డ్యామేజ్ ఉందో, మనకి ఎక్కడైతే పెయిన్ ఉందో అదంతా అబ్జర్వ్ చేసి రికార్డ్ చేసి బయటకు పంపిస్తుంది. అప్పుడు మనం డాక్టర్స్ ఈజీగా జబ్బుని క్యూర్ చేయడానికి మెడిసిన్ అనేది ఇస్తున్నారు. అలాగే ఒక రోబోట్ విస్కిసర్ అని చెప్పేసి ఒక రోబోట్, ఆ రోబోట్ ని పంపించడం వల్ల డైరెక్ట్ గా బాడీలోకి ఎక్కడైతే
presentation series optional
తీసుకున్నావు నువ్వు కాదు నువ్వు తీసుకున్నావు
optical nanomaterials.
Nanocoating studies about materials are studied in nanomaterials. Nanocoating is also preparation of cell to sensor. Nanocoating is also used for the harvesting. And that's why we have to platforming branch of nanocoating. He study about light interacting optical nanometers. Optical nanometers, because we so many things about optical nanometers. Nanometers and meters about which has one dimension 1 to 100 nanometer. Nanometer means 1 billion of nanometer. Nanometer is using batteries. Lithium ion batteries, solid state batteries, and sodium ion and zinc ion batteries. These batteries are used for storage energy, and nanometers also uses for capacitor. Carbon-based nanometers like graphene, carbon nanotubes. Graphene means layer of carbon atoms. Next topic, carbon nanotubes. Carbon nanotubes are single layer nanotubes and double layer nanotubes. Single layer nanotubes are one layer cylindrical shape of single layer carbon nanotubes. Multi-layer carbon nanotubes are two or more layer forming cylindrical shape of multi-layer carbon nanotubes. Nanomaterials and fuel cells. Fuel cells means plasma cells, palladium nanoparticles. Platinum and palladium nanoparticles are used in catalysis, oxidation reduction reaction. Catalysis means which is that in catalytic reaction, but is increase the efficiency of the reaction. Nanomaterials in solar cells. Solar cells like quantum dot cells, prostate nanometals, and plasmonic nanostructure. These are used for storage energy and aerobic solar energy. Chemical synthesis used for nuclear is a nanomaterial. Solar gel method uses chemical method producing oxide based nanomaterials. These are used for coating and catalysis. These systems approaches utilize biological systems, plants and bacteria fungi for sustainable nanometer production. These are used for environmental side, reducing water pollution and soil pollution. Conclude. Energy storage and conversion nanometers play critical role in developing efficient, sustainable power solution. These nanometers improve capacity, stability, and efficiency of devices such as battery, supercapacitors, fuel cells, ensuring long-term availability for energy storage. That's all. Thank you for everything.
Thank you, sir. Thank you, support. Now coming to parliamentary session, I request the principal and advisor of this seminar. I request Professor F.P. Chiriye Prasad, sir, Department of Physics, PR Government Degree College, Kakinada. And the convener of this seminar, K. Rajendra Kumar, sir, and coordinator of this session, P. Chiraju, and co-coordinator of this seminar, M. V. Srinivasa, sir, to come on to the dais. Please come on to the dais. I request, please come on to the dais. The participants, first, L. Sindela Reddy, second BSc Physics. Please come on to the dais. B. Park, Saparnam. Samarpan Priya, Government College, Kakinada. C.H. Ganga Bhavani, second MSc Chemistry. P. Mahalakshmi, Ideal College of Arts and Sciences, Kakinada. C.H. Durga Prasad, second MSc Chemistry.
D. Srinivas, MSc Physics, PR Government College, Kakinada. KV Venus Saitendra, third BSc MBE, PR Government College, Kakinada. M. Amrutesri, third BSc BD PR Government College, Kakinada. And R. Sakiti, PR Government College, Kakinada. P. Adilakshmi, first BSc, PR Government College, Kakinada. Now I request to Charlie ma'am, please. Yes, Vilas Reddy from second year physics. Please come. We call Samarpan PR Government College, Kakinada. Here, Ganga Bhavani, second MSc Chemistry. Please come on to the lab. I request Nageshwar also, please come on to the lab. Next, P. Mangalakshmi, IIM College of Arts and Sciences, Teacher Durga Prasad, second MSc Chemistry. Next, D. Shavani, MSc PR Government College, Kakinada. Please. Thank you, ma'am. Next, Kevin, yes, Saitendra, third BSc MBE, PR Government College, Kakinada. M. Amrutesri, third BSc, PR Government College. Next, R. Sakiti, PR Government College. Please come. P. Adilakshmi, first BSc, PR Government College, Kakinada. Thank you, sir. Thank you, Anika. Now I request Narayana sir, Assistant Professor of Physics, Chemistry, IIM College of Arts and Sciences, to wind up the seminar.
And thank you all for attending this today's seminar and made it success. Seminar section is started by inaugural speech by Professor D. Jayamohan Reddy, HOD of Chemistry. Hello. He gave speech on importance of nanotechnology and applications of nanomaterials. And then Dr. P. Former Senior Regional Director, Igma Nagpur. He gave seminar on carbon nanotubes, their classification and their applications. And during this seminar, he mentioned some interesting facts about the ancient Indian civilization. The property pieces of ancient India found some nanoparticles. And swords used in the 17th century also found some nanoparticles. And then next comes to the Professor C.H. Srinivasan, Department of Physics, Sati Institute of Technology and Engineering, College Rajabali Gura. He gave a seminar on nanosensors, humidity sensors, and various types of sensors in their applications. And then next to the Professor R. Balaji Rao, Head of Nanomaterial Department of Chemistry, Central University, Jammu and Kashmir. He gave seminar on energy storage devices, batteries and capacitors, and also giving some valuable information about the importance of cathode material manufacturing of efficient batteries. Then, next verse, session started by the magnificent speech by Dr. B. Satish Mohan, Director of Biochemical Solutions Private Limited, Visakhapatnam. He had a seminar on nanomaterials and their preparation methods, top-to-down and bottom-up methods. And then next comes to the Muslim Diction, Senior Scientist, CSIR, Chennai. He gave a magnificent seminar on direct materials and advanced computational approaches for electrochemical energy storage material design. And then next post-lunch session, Dr. Vishnu Shankar, Associate Professor of Chemistry, NIT Warangal, Telangana. He gave a seminar on nanomaterials and their manufacturing methods, solvent methods, and their applications in various sectors, industrial applications. Thank you.
And which she can interact it is time to express gratitude to all those who made this event a grand success. With that, we officially conclude the two-day national seminar on Convergence of Chemistry and Physics in Advanced Nanomaterials and Nanotechnology. We extend our sincere thanks to all the dignitaries, speakers, participants, and organizing committee members for their valuable contribution. We hope this seminar has provided insight and Department of Chemistry, there were vote of thanks. Good evening, Manita. The Department of Chemistry and Physics of IDS College of Arts and Sciences has successfully conducted national seminar on convergence of chemistry and physics in advanced nanomaterials and nanotechnology. Kumari M. Siri ma'am, inviting guests on dais. Thank you so much, ma'am. President of this program, Dr. T. Satyanarayana sir, giving opening speech on this seminar. Thank you so much, sir. Our beloved secretary and correspondent, ma'am, Dr. Chiranjeevi Kumari, ma'am, has given importance of nanotechnology and how it is utilized in present scenario. Thank you so much, ma'am. Convener of this program, K. Rajendra Kumar, sir, giving brief explanation about this seminar. Thank you so much, sir. My grateful thanks to Dr. Modi Dixit, sir, to inaugurate this seminar. And also thanks to Sri Ratnesh Kumar sir to
released the seminar proceedings. My special thanks to Professor B. Jagan Mohan Reddy sir to share their thoughts on what is nanotechnology. And my sincere thanks to Dr. P. Shivaswarup sir to give their presentation on carbon nanotubes. My grateful thanks to all resource persons and style persons who give their valuable speech on nanomaterials and nanotechnology. It is useful to students and all of us who are present online and offline. My heartfelt thanks to our esteemed advisor, Professor SPGVS, Professor for our guidance. Your guidance, wisdom and support have been instrumental in making this seminar grand. And also thanks to students who given their presentations on nanosciences. And finally, I would like to thank all the teaching and non-teaching staff members for your valuable suggestions, and also technical operators and students, press and media. Thank you so much. This program will be concluded with Telegram. Vindya Himachala Yamuna Ganga Uchala Jagati Taranga Tava Shubha Name Jage Tava Shubha Atisha Mage Gade Tava Jaya Gada Jaya Gana Mangala Same Jaya Bharata Bhagya Vidhara Jaya 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 Jaya
Jaya